I'm going to talk about multi-rail LNET Lustre. It's a joint development project from SGI and Intel. So multi-rail has been a long-standing request from the community, and it has been discussed in a few different ways, being multi-rail, interface bonding, or channel bonding. These three things are slightly different in how they get implemented. But what we've looked at is actually multi-rail element, and I'll talk about that today. So, what is multi-rail element? So, it enables us to communicate across multiple interfaces that are connected to one LNET network, rather than having to use multiple different LNETs or using InfiniBand in like an active-passive type configuration, ID bonding type approach. These interfaces are used simultaneously, and we take advantage of that by having multiple streams running at the same time. So we can get a very large aggregate bandwidth for a single client. So in big clusters with lots of server nodes and a limited number of OSSs within that configuration, we can actually have a performance bandwidth, and you can be deprived, those clients can be deprived of bandwidth within that configuration. So we can look at fixing that by adding faster networks, but that's quite costly. So we need to replace the HBA cards as well as replacing all the fabrics to get great bandwidth there. Or we can look at installing extra interfaces and creating separate LNETs and dividing up our clients across those two different LNET networks. So with multi-rail, each interface connects to a separate LNET network, but they work across those multiple interfaces. We can add multiple streams there. So we can increase the bandwidth to a single client in that system within that configuration. So the drive for that from an SGI perspective was to enable more bandwidth to very large clients. So SGI has a UV platform that is a single image system. We have a 32 sockets NUMA system as well as a 256 socket NUMA system with up to 64 terabytes of memory. So it's a very, very large client. Obviously, much smaller large clients can also take advantage of multi-rail element. But some of the problems with Lustre and very large clients, especially extremely large NUMA-based clients, is the PCI bus is connected to one of the sockets, and you've got a single interface card on there, and we are running a job that spans multiple CPUs or is running on a CPU that is over the NUMA link, we can actually get very low bandwidth from Lustre. And it has been a complaint from a number of our customers for a while about the UV not performing well with Lustre. And this is because we just can't get the bandwidth to be able to feed the UV effectively. So our goal was to increase the bandwidth from Lustre to deliver it to the UV and improve the performance of the UV platform. So the multi-rail Lustre project, basically we looked at multiplexing interfaces across, multiplexing across interfaces as opposed to driving them. And to take advantage of this, we need multiple data streams, which I mentioned earlier. It's also hardware agnostic, so we support all of the current fabrics that Lustre supports. It also enables us to use multiple fabrics as well, so you can actually have Ethernet and InfiniBand or OmniPath and InfiniBand within the one environment. And the large client can actually communicate across both of those networks to a single file system and take advantage of that aggregate performance. We've actually got peer discovery capabilities to simplify the configuration. So we can do automated discovery of peer interfaces as well as the multi-rail capability across those clients. So there's a bit within the configuration which tells us whether those clients are running a multi-rail capability or not. The configuration can be changed at runtime, which is very useful. This includes the adding and removing of interfaces, and you can utilize the LNET CTL tool for configuration purposes. And as long as the clients that you want to take advantage of the multi-rail capabilities need to be running the multi-rail patch, and so do the servers. but other clients that are not running the multi-rail patch can still function within this network. So there's no problems, there's full compatibility there. So there's no need to deploy the multi-rail configuration to all of the clients if they're not going to take advantage of it. And the added resilience for a variety of alternate paths. So there's two main types of configuration. So there's a static-based configuration and there's a dynamic-based configuration capability. Both of those still have a static configured component of that. So the local network interfaces and the selection points need to be statically configured, whether you're doing a dynamic configuration or a static-based configuration. The peer network interfaces, that can be done using the LNET CTL or can be done using the dynamic peer discovery capabilities. So the dynamic configuration basically sends an LNET ping packet across the network, and this creates a list of the peers' NIDs, and as I mentioned earlier, there's a feature bit that indicates whether those peers support multi-rail or not. The node then pushes that list out to the multi-rail peers so that everyone is aware of who is multi-rail capable within that LNET configuration. So use cases improve the performance, so improve single client performance within a configuration, improve the resilience by enabling having multiple interfaces on a single host, or even having multiple different network types within that configuration. And the multi-rail code is also numer aware, so that's really important for very large clients that are working with very large memory. So we have fine-grained traffic control, as well as simplifying multi-network file system access. So some example configurations. So if we think about a configuration without multi-rail, we have a really large client that has a single interface to our configuration. And effectively that is our congestion point, because we want to try and get as much data into that big client as quick as possible so that we can take advantage of that large memory and all the sockets within that single client. So this is a problem, and it effectively makes that big client perform very poorly, and you're not taking advantage of the infrastructure that you have. Excuse me. So if we look at how we can improve that without using multi-rail LNET, we can actually have multiple LNETs configured within that single fabric and add multiple interfaces to the big client. But this adds an administrative overhead and configuration complexity that you then need to manage within that environment. So each OSS is living in a separate LNET network in this particular example within the single fabric, and each interface of the big client is connected to each of these different LNET networks. So you're not actually taking advantage of the aggregate capability without really fine-grained control of what data you're pulling into that box across which Lustre networks. So now with the multi-rail patch and a single fabric, we've got the large client with multiple interfaces connected to that single fabric, running the multi-rail code, as well as all of the Lustre servers running the multi-rail code. So the LNET configuration now allows for all of those interfaces in the big client to work collectively across that single fabric, and it enables it to get the aggregate bandwidth. It's a much simpler configuration because we're not having to define all of those different networks and try and do the manual fine-grained control of traffic into those large clients within that configuration. And there's no longer a congestion point within that big client because we've got the control of multiple interfaces to spread that across. So we can also take advantage of configuration where we utilize two different fabrics, and these two fabrics could be the same type, so they could both be InfiniBand, or they could both be OmniNet or Ethernet, or one could be Ethernet and one could be InfiniBand or Omnipod. So what you've got in this configuration is the UV itself has a couple of interfaces connected to one of the fabrics, a couple of interfaces connected to the other, and the clients themselves are divided across those two fabrics. And that may be because of the interfaces that are available to those clients, or it may be a logical separation of the clients so that you actually are dividing up the bandwidth between those two fabrics. So the server nodes themselves are connected to both of the fabrics, so we have the single global namespace that is actually shared across those two different fabrics within that configuration. And the big client itself is able to communicate across both of those fabrics to the same file system. And this gives us a greater aggregate bandwidth within that configuration, as well as the resilience of maintaining connectivity to the big client in case of a fabric failure or even congestion in that particular fabric. So in a more complex configuration with multi-rail LNET, we have a single fabric with multiple switches within that fabric. And what we get within this configuration is between the two fabrics is what can potentially become our bottleneck. So client 1 and client 2 are okay when they're communicating by themselves through their same switch, but if there's any type of cross communication that has to go between those two switches, there's potential performance degradation within that configuration. So if an OSS loses a connection to one of those fabrics, now the traffic that needs to go to that, those set of OSTs that are managed by that OSS, by OSS1 in this configuration, will now have to go across that red link. So if we've got a large number of clients that need to access data within those OSTs, all of a sudden we're sending all of that traffic across that interlink connection. So that could be a potential bottleneck within the configuration. So if we add the big client within that configuration now, with interfaces connected to both of the switches within the single fabric, even if we have the even if we have the OSS connection fail, like in the previous example, the big client can still prioritize traffic down the optimal path to the switch that has a direct connection to the OSS, avoiding the red link on the diagram here. So it's not getting starved of bandwidth or fighting for available bandwidth with other nodes within that configuration. So project status update. So basically there's a link there for the multi-rail LNET project, so you can actually have a look at that and see how it is. The patches are there to enable static configuration, and they're under review in relation to landing into the Lustre community release. This slide is actually a little bit out of date because it has been flagged as landing in Lustre 2.10 in the community release. Initial unit testing has been completed on smaller configurations and have some results of that I'll show in a second. Also, the dynamic peer discovery stuff is still being fine-tuned. So static configuration is fully functional at the moment and is actually available today from SGI. So if anyone's actually interested in that, please come and have a chat to us because we do have early access to the multi-rail LNET today, and the results are really promising for that configuration. So what I will note here is this test was done on older hardware, and when I say older hardware, these IS 5500s are around 5 years old, so they're quite old disk arrays, and the UV2000 is our previous generation large node. This was purely for functionality testing rather than performance testing, but obviously we're trying to get the maximum performance out of that Lustre file system configuration. So we've got 160 sockets, or 16, it says nodes, but it's 16 blades within that configuration, and effectively 4 FDR connections to the FDR fabric. The OSSs are connected to that, and we have a total of 30 OSTs within this configuration, and it's a fibre channel based back-end to the physical storage arrays, of which there's 5 IS 5500s. Each of those IS 5500s are capable of up to a maximum of about 3.5 gigabytes per second. So there's a total of approximately 17 gigabytes per second of bandwidth available within this configuration. So through the testing that we did, we were able to get up to 16.5 gigabytes per second performance, which is almost at the theoretical limit of the disk array configuration, or 3 times the FDR rail speed. So this is really promising. Further testing is going to be done at scale, so we're trying to scale this up across more interfaces. The initial projection easily get up to 16 interfaces that we could actually run that we'd like to test.